All right, and this, grab my pens. In this second version of Prochirality, we're going to determine is HA Pro R or Pro S? So just as in when you have a chiral center, right? So that's a chiral center. We should be able to designate that R or S. However, what's the priority here, X or H? And the answer is X is sort of indeterminate, so who knows? So the rule, how you do this, we've established, again, this is Prochirality 2. If you haven't seen Prochirality 1, go back and watch it now. So assign priorities. I'm going to get rid of HB. So assign priorities to the groups. All right, HA and HB are obviously low. Methyl is bonded to 3, so carbon and carbon, 3 H's, 3 C's, so this is CCC and that's HHH, and so this is gonna, so this will be 1, this will be 2, and then HA or HB, what do we do there? Well, the way to determine if a chiral center, a prochiral center is Pro R or Pro S is to say HA 1 higher than HB. So HB will be 4, HA will be 3. Okay, so we're just saying that HA is 1 step above HB. So if these were two, you know, if these two tied for first, say that we had 2 oxygens here, what we would do is basically say one of them is 1 and the other one is 2, and then we'd go from there. But with H's, it's easy. Just basically make the one you're not testing number 4. Okay, so this gives us then 1, 2, 3. 4 is back. That's a counterclockwise circle, and so HA then is Pro S. And so like I said before in Prochirality 1, there might be an enzyme that has an affinity or a selectivity for the Pro S proton. If it did, it would only take HA. If it had an affinity for Pro R, the Pro R proton, it would only take HB. And so there are a lot of enzymes like this that remove a proton from a molecule and replace it with something else and make a chiral center. Again, because all of the proteins that are involved in that are chiral, you tend to get really high selectivity. And so this concept is pretty important to know. Very good.